All right, in this video, we're going to be working the Unit 4 practice test, which is a practice test on vector fields for multivariable calculus. And we're going to start off with, is it conservative? This is a vector field in the plane, so I know that for a two-dimensional vector field, I know I'm just checking, is my equal to nx? Okay. Well, my is going to be equal to the derivative of sine x with respect to y, and that's going to be 0. And x is going to be equal to the derivative of this thing with respect to x, and that's going to be e to the y. And these are not the same thing, therefore I'm going to say it's not conservative. Okay, for part B. Compute the integral over c of f dr, where c is the elliptical path shown in the figure. Okay, well, I think we're going to need to first parameterize c. So c is going to be, okay, we know how to parameterize an ellipse. I've given you some practice on that recently. Okay, if it goes 3 in the x direction, x is going to be 3 cosine t. And if it goes 2 in the y direction, y will be 2 sine t. And this will be, because it's just the first quarter of it, this will be t running from 0 to pi over 2. Then, so I'm going to say the integral of over c of f dr is going to be the integral from t equals 0 to t equals pi over 2. F of r of t is going to be, all right, well, it's sine of x, and that's sine of 3 cosine t. It's a strange function, but it's not the end of the world. And then x e to the y. X, 3 cosine t. E to the y is e to the 2 sine t. Okay, and then dr is dx dy, which in dx dy is x prime of t dt. So cosine t dt. And then this one is, wait. dr is, goodness, pardon me. Reach for my homework stamp. That was not going to be what I needed. Yeah, I took the derivative of the wrong thing here, right? dr is dx and dy, where this is x and that's y, so it's going to be negative 3 sine t and 2 cosine t dt. And then I'm going to actually make this happen, and I'm realizing I need to be very careful about how wide I write, because I need to fit all of this. So okay, plus 6 cosine squared t from 2 powers of cosine and e to the 2 sine t. Now, this one, we don't want anything to do with that. We're going to, bring out a friend here, and I'm going to make sure it's in function and radian mode. Pre-cal discussion in here this morning and had to go into parametric mode. Anyway, we're just going to type this in. Integral 0 to pi divided by 2, negative 3 sine of t times the sine of 3 cosine t plus 6 cosine squared t e to the 2 sine t. I'm just going to scroll back through and make sure that I've closed off all my parentheses, because the place where a minor tragedy could still occur. That's going to be 10.702. Well, that's the path integral. Okay. Number 2. looks like we've got a vector field in space, and we're going to start by finding the curl and divergence. Okay. Now, if you don't have a formula sheet and you don't have the formula written down, you remember curl is del cross F. Okay. But if we've got the formula, we don't need to go through that whole process. That's pretty much for you. Maybe for next year when you are not allowed a note sheet or something, if you were in a class that doesn't allow one of those, this would be mz minus px, and then this third one would be nx minus my. And so knowing this, I can just figure out what all of these partials are. This is going to equal, okay, py minus nz. Py, that's going to be 0, minus nz, also going to be 0. Okay, mz, no z's up in this first component. Px, that's the third component, no x is there. Okay, so this is, I think I'm seeing a pattern emerge. And then nx is going to be, with respect to x, this would be 6x to the 2 y to the first. And my is going to be 6x to the 2 y to the first. Okay, and so this is the 0 vector. Okay, now I know that when I see that the curl of f is the 0 vector, I know that means that f is conservative. Okay, I'm just going to throw that out there. Okay, divergence of f is del dotted with f. And, in case you have that written down, that's mx and y and pz. Add it all together. And so I can do that. Mx is 6x y to the 2. And y is going to be 2x to the 3. And pz is going to be negative sine of z. Okay, that's it. So that's 2a. And we haven't really, I'm just going to throw this out there, we haven't really done anything with divergence in this class, and depending on how far we go into vector analysis, we might not actually work with it all that much. But it is the type of thing that does come up later. If you go and do a lot more surface integration, you look at kind of some theorems related to that, Stokes' theorem, divergence theorem, all that stuff. It would come back, I just don't know if we're going to do that this year. So compute the integral over c of g dotted with dr. Okay. Well, I know, look at this curve. This is a horrible curve. Okay, you can see there's very little hope of parametrizing this one. I guess we could parametrize it in a bunch of really small pieces, but that doesn't look fun. What we can do is we can say, hey, I found this thing's conservative, so I know that the integral's independent of path, and I could, on one hand, I could parametrize that path right there that I just drew in red, and then run the path integral that way. But I think the more clever way to do this is to use the fundamental theorem of path integrals. So I'm going to need to find a potential function for g. Whoops. I was supposed to be finding the curl and divergence of g. Yeah, same thing. All right. So a potential function for g is going to be, all right, so I'm going to call it lowercase g. G is going to be an antiderivative for 3x to the 2 with respect to x, which is going to be x to the 3, y to the 2, maybe plus some other stuff. Okay. It's also equal to an antiderivative of 2x to the 3y on y. Okay, and that's going to be, well, an antiderivative for 2y would be y squared, so it'll be x to the 3, y to the 2, maybe plus some function that depended on x and z. This one could have, some other hanging on stuff, but we're going to see that there's not going to be anything else. Okay, and then it's also going to be an antiderivative for cosine z with respect to z, so that would be sine z, plus some function that could depend on x and y. Well, there it is right there. That's the function that depends on x and y. These are overlapping, so my potential function is g of x and y and z is equal to x to the 3, y to the 2 plus sine of z. And you can take the gradient of that and check that it is a potential function. There is plus a constant out here. I'm going to just take that constant to be 0, though. Okay, so I'm going to say that this is going to be equal to g at the end point, which is 5, 1, 0. So g of 5, 1, 0 minus g evaluated at the starting point, which looks like 1, 4, negative 3. Okay, and then we're just going to plug these things in. Who knows what sine of negative 3 is, but we'll just probably leave it as is. So g of 5, 1, 0, so 5 to the 3 is 125 times 1 is 125 plus the sine of 0, that's going to be 125. G of 1, 4, and negative 3, x to the 3 is 1, y to the 2 is 16. Plus the sine of z. And that's going to be a safe place for us to stop, right? All right. Okay, I should not have had my email up in the background. Received a message, got distracted by it. I shouldn't do that. Okay, that was part B. Yeah, we're good there. All right, and number 3. Oh no, that's my setup. Curve A is, yeah, perfect. All right, curve A is parameterized by r of t. Compute the integral of f, the path integral of f over curve A. Okay, so I've got A parameterized by r of t. F of xy is xy plus 1. So I'm going to need f of r of t. All right, so xy, I guess that's yx, that's the same thing, plus 1. Okay, ds is equal to the square root of x prime of t squared plus y prime of t squared dt. So that's going to be 3t squared minus 4 squared plus 2t squared square rooted dt. And so the integral over a of f ds is going to be the integral as t runs from negative 2 to 2 of f of r of t ds. Okay, so and this is going to be just totally a job for the calculator. And this is 3t squared minus 4 squared plus 2t squared dt. Hold on. Okay. I guess I'm aware. Negative 2 up to 2. Okay. T squared minus 1 times t to the 3 minus 4t. Close off that one, add 1. And then multiply that by the square root. Okay, that was a lot of typing. It's going to definitely need to think for a second. 15.694. And, well, that's great. That was 3a. What's 3b? Oh, okay, this is integrating a vector field. Oops, let's turn that paper around and... Yeah. So 2y dx right? 2y is that. Dx is x prime of t dt. So that's 3t squared minus 4. And then I'll just hold on to the dt for later. And e to the x, so negative e to the x dy, e to the t to the 3 minus 4t. dy is y prime of t dt, so that's times 2t. Then we'll factor out the dt's, integrate that from negative 2 to 2. And again, this is not something we want to compute by hand. So I'm going to go ahead and call this integral from -2 to 2 of 2 times t squared minus 1 times 3t squared minus 4 minus e to the t to the 3 minus 4t multiplied by 2t dt. 79.025. Okay, that was number 3. All right. Number 4, B is parameterized by this. Let G be that. Oh, okay, yeah. Okay, here's a good couple of problems. So for A, G ds, okay, well, G is xy plus square root of z. Xy plus the square root of z. Okay. So that's going to be t to the 3 plus t to the 3 halves. Yeah, and then what else is going to happen? Oh, ds, yeah, is the square root of r, or like it's the length of r prime of t dt. So it's going to be the square root of 1 plus 2t plus 3t squared, all squared. dt, meaning that the integral over curve B of g ds is going to be the integral from 0 to 2 of g ds. Okay, I left off a squared there, but I know that the derivative of t to the 3 with respect to t is 3t to the 2. And so plus, and if I squared 3t to the 2, I'd have 9t to the 4 dt. Definitely a job for the calculator here. T to the 3 plus t to the 3 divided by 2. Close that parenthesis, start the square root. 1 plus 4t squared plus 9t to the 4 dt. 51,536. And 4b. Okay, compute the integral of the gradient of g dot dr. Okay, that's going to be another fundamental theorem question. This one's going to be hopefully really fast. Okay, yeah. So yeah, so this is going to be, okay, the gradient is vector field, and it's definitely conservative because it's the gradient of g. And so this is going to be g at the point where, okay, when I plug in 2, I'll have 2, 4, 8. And at the starting point of the curve, I'll have 0, so it'll be g of 0, 0, 0. And that's going to be, okay, yeah, you cannot see. It's xy plus square root z. So xy plus the square root of z minus xy plus the square root of z. And that's going to be it. It'd be 8 plus the square root of 8, which, yeah, whatever. Lost myself, but oh, that's all for that problem. Okay, so let's switch this over. And all right, so I almost got this problem just right, but I don't think it's quite to what I'd hoped. Okay, I kind of hoped that that this was irrelevant. It is going to be relevant. We'll have to use a calculator for it, but I think you can see how I can make this problem a little bit simpler. So curve C comprises part of the boundary of R. find the integral over curve C of f dot dr. Okay, so we're going to use Green's theorem here, right? That's why they gave us the area of the region. So what I know from Green's theorem is that this integral, oh, maybe if I forgot, this is not a completely closed loop, so I need to bring in another piece of curve, and maybe I'll call that D. Okay, so Green's theorem tells us that, I'll just start over here. The integral over the closed loop C plus D of f dr is equal to the double integral over the enclosed region, that's R, of nx minus ny dA. Okay. Now, nx 0. Okay. So nx is 0, my is 10, so that's negative 10 dA. Okay, I can factor out the negative 10. Okay, the double integral of dA is just the area of region R, so that's negative 10 times 10.3 is negative 103. Okay, but this isn't exact, this is the integral over the closed loop C plus D. So what I need to do is I need to find the, oh, I didn't draw it, but I think, we're assuming this counterclockwise orientation. Pardon me. I thought I had drawn that in when I made this figure. Okay, but now you can really see it. So that's negative 103, or 103. But we're also interested in, actually, not supposed to see that. This is also equal to the integral over curve C plus the integral over curve D. So maybe I'll pull that out in like blue or something. Okay, so if I add these together and I get 103, and this is the thing that I'm trying to find, I know I'm going to take this negative 103 and I'm going to subtract the integral over curve D of f dr. And we can do that. Okay, so the integral over C of f dr is going to be the double integral minus the integral over curve C. No, over D, pardon me. Okay, now to get D, we're going to need to get that integral, we're going to need a parameterization. Not going to be too hard. R is going to be, all right, the x-coordinate is always 3. The y-coordinate is running from 1 to 5. So I think that's 1 plus t as t goes from 0 to 4. So that would be minus the integral from 0 to 4 of f of r of t is going to be, right, f is 10y. So that's 10 plus 10t, and e to the y sine y, e to the 1 plus t sine of 1 plus t, and dot that with dr, which is x prime of t dt, that's 0 dt, and 1 plus t, its derivative is 1 dt. Okay, so right, and so I'll rewrite this one more time. Yeah, you got enough room to see what I'm doing here. So that's e to the 1 plus t sine of 1 plus t dt. That's going to require a calculator, and so I'm going to do that. That was negative 103 minus the integral from 0 to 4 of e to the 1 plus t sine of 1 plus t dt. That's surprising. Okay, I didn't expect this integral to come back a large negative number, but yeah, starting at sine of 1, going to sine of 5, that is probably going to be more negative than it is positive. I guess I could see that integral coming back negative. Okay, so that's negative 10.383. But there, yeah, I think you can see that there's probably ways that if I was a little more careful through, these things, I could probably make this integrand come back to where it would be much easier to compute. But that wasn't so bad because you're definitely going to have a calculator on the upcoming test. So that's all the problems, and so that'll be all for this video. Thanks for watching.